Any complex linear circuit can be reduced to a single voltage source and a series resistor using Thevenin's method. But the same circuit can also be represented in a completely different way using a current source model. In this video, you'll learn Norton Theorem and why it provides an equally powerful but alternative perspective in circuit analysis. Norton Theorem states that any linear two-terminal network can be replaced by an equivalent current source in parallel with a single resistance. From the perspective of any external load connected to those terminals, the electrical behavior remains identical to the original complex circuit. This means voltage-current relationships at the output are preserved even though the internal structure is simplified. This idea is extremely powerful because real circuits often contain multiple sources, resistors, and interconnected networks that are difficult to analyze directly. By converting the entire network into a simple current source model, engineers can focus only on how current is delivered to the load rather than solving the full internal structure repeatedly. At its core, Norton Theorem is not changing the physics of the circuit, it is changing the way we represent it. The external behavior stays the same, while the internal complexity is replaced by a mathematically equivalent model that is easier to analyze and reuse across different load conditions. A Norton equivalent circuit is fully described by two parameters, Norton current and Norton resistance. The Norton current is defined as the short-circuit current flowing between the two output terminals when they are directly connected together. This value represents the maximum current the network can deliver under ideal loading conditions. The second parameter, Norton resistance, is the equivalent resistance seen from the output terminals when all independent sources are turned off. Voltage sources are replaced by short circuits, and current sources are replaced by open circuits. The resistance calculated from this perspective is identical to the resistance used in the Thevenin equivalent. Once these two values are known, the original circuit can be replaced by a current source in parallel with a resistor. This simplified model behaves identically to the original network as long as it is observed from the same output terminals. Norton and Thevenin theorems describe the same physical system using two different mathematical representations. A Thevenin equivalent uses a voltage source in series with a resistance, while a Norton equivalent uses a current source in parallel with a resistance. Both models are interchangeable and represent identical terminal behavior. The conversion between them is straightforward. The Norton current is equal to the Thevenin voltage divided by the Thevenin resistance. Likewise, the Thevenin voltage is equal to the Norton current multiplied by the equivalent resistance. This direct relationship allows engineers to switch between models depending on which form simplifies analysis. This dual representation is extremely useful in circuit theory because some problems are easier to solve using voltage-based reasoning, while others become simpler using current-based reasoning. Engineers choose the representation that reduces complexity and improves clarity. In practical circuit design, Norton equivalents are widely used in systems where current behavior is more intuitive than voltage behavior. Parallel networks, current dividers, and multi-branch systems are often easier to analyze using Norton models because current naturally splits across parallel paths. Engineers also use Norton equivalents when modeling active devices such as transistors in small signal analysis. Many semiconductor devices behave more naturally as current sources, making Norton representation more aligned with their physical behavior in certain operating regions. Simulation tools frequently convert circuits internally between Norton and Thevenin forms to optimize computation and simplify analysis. Understanding both representations helps engineers interpret simulation results correctly and choose appropriate models during design. In RF engineering, Norton equivalents are especially useful when dealing with signal sources, impedance networks, and parallel circuit structures. Many RF systems involve multiple signal paths where current distribution determines overall performance. Small signal transistor models often use current source representations, making Norton-based thinking essential for amplifier design and impedance matching. In these systems, understanding how current flows through different network branches is critical for predicting gain, stability, and signal integrity. Together with Thevenin theorem, Norton theorem forms a complete framework for equivalent circuit analysis. This framework allows RF engineers to simplify complex systems into manageable models while preserving essential electrical behavior across frequency-dependent networks. So today, we learned that Norton theorem allows any linear two-terminal circuit to be represented as a current source in parallel with a resistor, providing an alternative but equivalent way to simplify circuit analysis. It is mathematically equivalent to Thevenin's model, but often more convenient for current-based analysis and parallel networks. In the next lesson, we'll explore source transformation and learn how to convert seamlessly between voltage and current source representations. If you found this useful, like the video, subscribe, and follow for the next lesson.